On this test, it's test 10, as Reese just said. Okay, the sections are from 19.3 all the way to 21-2. 19.3 was about power. There it is, power. Okay. In power, we had conceptual and mathematical both. Now, conceptually, what is power? What is power? F.
The rate of
There's more than one definition, yeah?
it's the rate of thing.
Rate of what thing? It's a rate. Reese, help her out.
Work over time.
It's a rate at which work is done, or work over time, as Reese said. Now, remember, when we talk about the rate at which work is done, it's an easier thing to say for mechanical. For electrical, we could say the rate at which energy is transferred, or energy moves. Okay, so power, remember our definition conceptually was the change in energy over a given time period. But we came up with 3 formulas from this. Give me one of those formulas, Mike.
P equals plus V squared over
V squared over R. Good. What is the other formulas? Give me two more. Joyce, give me one. Good. And the third one? The third one, anybody remember? It's on your formula sheet. If not, I squared R. Okay, 3 formulas. Now, how do you know which formula to use? How do you know which formula to use? I got to use it.
Just like by what given.
Yeah, based on the scenario. Based on the scenario, you know which one to use in this problem, okay? Mike.
I'm just confused because P equals. Oh, never mind. I thought V and R were the same thing.
Okay. Alright. So, in these problems, remember how you came up with a resolved circuit just now in the lab? What was the resistance? Was it 51.3?
Yeah.
Does that sound right?
Yeah.
So your final circuit looked like this at the end? And what was the voltage on the battery? 3 volts? Alright. So 51.3 ohms and 3 volts. The symbols here. Alright, now, if I were able to do this, I now have the voltage and the overall resistance. So if you want to find out the power that is needed for an electronic device to run or to work, if you can find that device's equivalent resistance, you now have equivalent resistance and voltage. You can use the first formula to find out the power needed to run that appliance. Okay? So when we talk about equivalent resistance, it's not just a tedious exercise for no reason. It's so you understand the idea that when you have resistances, you can think of them as a lump sum. Right? So there are many different small resistors in a circuit. But when those resistors are considered as a whole, 51.3, we can find the power. Okay? The power. Power, what are the units? Not joules. Joules per second, which is what? W. What does that mean? Watts. Okay? W is watts, okay, for power. So here, if we found the power, it would be voltage squared over resistance, so 9 over 51.3 units of watts. Okay, W is for watts, not for work. Okay, work is measured in joules. So 19.3 is conceptual and it is also mathematical. Now, I might ask you a power question as like a part B after you've simplified the circuit. You follow what I'm saying? So maybe I ask you to do a reduction of a circuit, like a complicated one like you do in the lab, and then at the end say, now find the power. So it'd be like a part B. There's not much to power stuff with these mathematically, okay? It's going to be like one question most. F. I haven't made the last 4 questions. I know what they're going to be about. So I'm thinking it'll probably be either 90 or 100 points. It'll be, for that range, not like a 70-pointer. Okay? 20-1. What was 20-1 about? Schematics. Okay, schematics. What is a schematic? What is a schematic, Philip?
It's like a diagram showing Circuit, basically.
Perfect. A schematic is either a blueprint of a circuit or a diagram of a circuit. It's not just a blueprint, because a blueprint is thought of as a mechanical blueprint usually, but it's some sort of electrical blueprint or a diagram of a circuit. That's what a schematic is now. For section 20-1, we talked about a few, look at your notes please. We talked about a few different instances. We talked about things like closed and open circuits. We talked about shorts in circuits. What is a closed versus an open circuit? F.
When the open, make it work,
What do you make of what?
like light up and work.
Think about open as ready. If I open up a switch,
That's
now
what
there's no flow.
Yeah.
Turns it off.
Yeah, that's what I mean.
You said it would make it work.
Close and make the whole, close and make the lights work.
Yeah. Okay, you said it backwards the first time.
Oh, wait.
So open makes it not work. Open, when the circuit is open, the lights are off. It's
That's
not
like
working.
open. Oh.
When the circuit is closed, the lights are on. Okay? What's a short circuit? What's a short circuit or a short in a circuit? Reese?
Is that when you don't have any resistors?
Yes, that's exactly what it is. It's a circuit with no resistors in it. So there's nothing to bear the load of the battery. Okay, you need a load-bearing element. You just have this. There's no element there. So what's going to happen as a result? The wire is going to heat up and eventually melt. Okay, if there's enough current flowing through it. Today, in your lab, the voltage was so low that there's almost no current flowing through there. Very little potential difference. So you don't feel that significance. Like,
What if you just left that on for like a week?
what'll happen is either one of two things. It will reach a temperature where it will burn or the battery will just drain.
Okay.
If you leave it connected like that in a short, the battery will continue to run, move charge carriers, but nothing will happen. It'll drain the battery. If it gets hot enough, it might melt. Okay? It depends, really. It's tough to answer that without seeing. All right? Elliot?
So in the diagram, it goes positive to negative.
Yes, that's a good point. Flow always moves from positive terminal to the negative terminal. Because we look at positive flow. I know it's counterintuitive, but it was just the way it was thought of, and it's the way it's always taught, even in college. So I'm not going to deviate from that, even though it doesn't make much sense. Because you would think about electrons flowing.
What the positive side is what the negative electrons are. And then you can attract them to the
We think of it as this. We think of it as the charge carriers have a lot of energy at the positive terminal, and they need to move. They move. They hit the load-bearing element. Right? They hit the resistor right here. They lose all their energy, and now they have low energy, and the low energy causes them to go back to the terminal with low energy. Then they get work done on them by the battery, and they charge back up. Okay? That's theoretically what you think of. Realistically, it's a little bit different, obviously, because you're looking at the flow of the electrons, really, that are moving. Okay? Section 20-1 and 20-2. 20-2 was about series and parallel, right? Those examples we did are perfect examples. They're perfect examples for the mathematical part on part 3.
The lab?
No. In 20-2, we did 2 examples. One in all series, one in all parallel. And we found like the voltage across each resistor when it was in series. We found the current in each resistor or each branch when it was in parallel. Those are great examples, okay? The section 20-3 is like what you did at the very end of the lab. That last one, where part of it was series, part of it is parallel. That's another great example. So you could probably guess as to what your 3-part question or 3 questions are going to be at the end. Okay? Series, parallel, combination. The power component will come about in one of those problems. Okay? I might add another question with power, but probably not mathematical. It would be conceptual. Make sense? All right? Let's do a complicated circuit together. All right? Let's do one together.
Why do you always use a black background for
I use the black or the green one. The other class used the green one, so I know the different sections.
Okay.
Yeah. I mean, I label them number-wise, but if I look at the video quick, it's also easy that way. All right, let's look at this one. Okay, let's put a switch over here. Say the switch is closed. Okay, what does an open switch look like on a diagram? Yeah, you get like an angle, right? So an open switch, let's show an open switch together here. Okay, it's an open switch.
What happens if one, like, could it be like one is closed and then the other one is?
Well, the switch has to be connected to one of them always.
That's
So it's on like a pivot. Yeah, it's on like a little hinge. Okay, and then it closes. You know, circuit at least. In your circuit, it was just pretty much no connection, connection. Okay, so let's close the circuit. When we close the circuit, we get rid of that. We put a little closed circuit there. All right, now, why is a circuit, before I get to this, why is a circuit breaker the same symbol as a switch? Because that was in one of your homeworks, remember? Circuit breaker, or was in the class or something?
Aren't they like the same as
No, not the same resistance. Elliot?
The circuit breaker kind of the same thing as a switch.
Yeah, because it is. That's exactly right. How does it work? What do we say? How does the circuit breaker work?
If there's too much current,
Good.
it like flips open so that it stops the battery from flowing and everything.
That's exactly right. When there's a surplus of current, it senses that current and it pops the switch open. So when you go to your circuit breaker, you're turning the switch to close the position. You're turning the power back on by closing the circuit or closing that switch. That's what you're doing when you go to pop the circuit breaker back on. Let's resolve this. Now, what do I look for right away to help me? Okay, so start with parallel, that's fine. So where do you see parallel? Follow the circuit.
right there?
Yeah, see this junction? Right away it's some parallelness. Now, there's another junction, right? So that's also something in parallel. But what about these two right here? What are they? They're series. Let's give numbers. Might help, right?
Wait, so is 7 in a series as well, or?
Well, that's what we're going to talk about next. So these two are definitely in series. Let's make them 3 and 5 instead of 3 and 4. Because then they'll add up to 7. I don't want them to add up to 7.
Is 2, 3, 5, 7 not a series? Parallel?
These are in series, right?
Yeah. But
Okay,
they're-
and then we'll talk about the others in a moment because it's an odd situation. Give me a second, okay? Let's combine the ones in series and let's redraw the diagram. I want you to do this every time, please. Don't get lazy and try and cross stuff out. Okay, that's what we've got right now. Why did I put an 8? 5 and 3 is 8. And 5 and 3 are in series. Now, this is to answer Ev's question. This is complicated, and I purposely did this. Take a look. We definitely have parallel circuits, right? And parallel circuits usually happen when there's a branching off. But how many branching offs are there? Yeah, there's 2 here. I mean, there's obviously 4, but those are the mirror image. But take a look. Follow the circuit. This branches. So this resistor is in parallel with this whole thing. So we need to then go to this whole thing and think about what this is. This branches off right here, which does what to the circuit?
Parallel.
What's parallel? Only 8 and 7 first. Then the result of 8 and 7 in parallel is itself in parallel with the 2.
Okay.
Again, let me show you. Watch. Watch the board if it helps. It branches off right here. So this 2 is in parallel with whatever goes from here. But what goes from here is this whole thing. So this whole thing is in parallel with the 2. So we need to resolve this whole thing first. Because look, it branches off here. So this 7 is in parallel with the 8. So let's do these in parallel first.
Those are like parallel inside parallel.
It's exactly right, Mike. Parallel within parallel.
Is it, like,
Okay, that's what we start with.
Does that do anything different to like the current
overall thing. Yeah, absolutely. As opposed to them all being in parallel, you'll get a completely different answer too. All right, so what do we get? 1 over 8 plus 1 over 7. Give me a number, please.
Well, sorry, that's 20%. You get 0.267,
8, 9.
And then RQ is? Inverse
3.7.
3.7. So I draw my circuit again. Now, here's the 2, here's the 5. How am I going to draw this now? How am I going to draw this now?
You do a parallel thing from 2.
yeah, then you add.
Okay, again, the 8 and 7 have combined to become that 3.7. And the 8 and 7 together as an entity are in parallel with the 2. So we write the 8 and 7 by itself as the 3.7 that we got. Now what do we do? Yeah, the 2 and the 3.7, they're parallel now. So let's work on these. Leave the 5 alone again. It occurs before any branching off. What do you get as a decimal with a half and 1 over 3.7?
Sorry, 0.77.
Okay, so REQ comes out to be?
1.3.
Is that right?
Yeah.
Okay, so that's our REQ for these two. The REQ is 1.3. How do you have an idea that you're doing it right? How can you check? What's a sanity check?
The number.
Okay.
It's gonna be less
Should
than.
it be like 1, 2, 3, 1, 0, 1?
What is it?
It's gonna be less than.
Yeah, the two that you used in parallel, this has to be less than either of them for sure. See, 1.3 is less than both of these. 3.7 was less than both 8 and 7 that was up here. The result in parallel is always going to be a lower resistance. Whereas the result in series is always going to be a higher because you're adding them together. So let's redraw our circuit. Okay, now these are in series. Finish it off for us. Just add them together. And obviously in series you don't have to show work. So this equivalent circuit represented all the things that we had in the beginning. So again, if I wanted to find the power at this point, or if I wanted to find the current in the system, you can use V equals IR to find the current. You could use P equals IV or P equals V squared over R to find the power. Elliot.
I'm not sure, it was just a coincidence, but I did it the wrong way the first time, like where you do like 1 over 2 plus 1 over 8 plus 1 over 7, and I got pretty much the same answer.
Let me see, because
Wait,
it's parallel within
I
parallel.
know, I'm not, it's probably just a coincidence. It's like 1 over
The last class we did an example where if you did it that way around, it didn't work.
Maybe it's just.
But we didn't do parallel within parallel. We did two separate parallel parts. And we had to do them separately and then put them together, or we'll put them all together at once. That's a good point. All right, so Elliot made a point. Take a look. If you did parallel within parallel as 1, 3 networked parallel, you get the same answer. Now, here's the reason why. But that's just rounding, I'm guessing. But I realized why. In the other class, we did an example. Look at the other video if you want to see the other example. But imagine if you had something like this now. In the other class, the question was posed, could you put these four in parallel since they're parallels? But here you can't. Okay? So you'd have to do these two in parallel first. Okay,
Why would you do that to begin? Like, why was that even a question?
because he said, and his point actually worked. Remember there was a parallel within a parallel?
Yeah.
If he did it with all of them like 1/2, 1/8, and 1/7, all of them together, and it worked. Because that was a parallel within a parallel. This is not a parallel within a parallel. Okay? So here you'd have to do these two, get a resistor. Do these two, get a resistor. Then you would have a resistor over here and a resistor over here. Okay, and those would be in parallel with each other.
That's like greater than everyone. That's like this series, right?
You want to stop?
Yeah.
This is in series with whatever you get here. You then add those two, get one resistor, make these one resistor,
Technically, it's
then
like
these
two-
are in parallel.
It's like two resistors, like two circuits together.
Yeah, that's what this one is, more like two circuits. Yep. Nice point, Elliot. Good point.
Wait, and then you would just add them though, right? 'Cause once you
So you would do this, Mike. Ready? This would become this. One resistor over here as a result.
Yeah.
Over here you still have the top one. One resistor here. Then you would go ahead and simplify the left-hand side, right? To one resistor, because they're in series. And now these are in parallel. So you do these in parallel, because the branch right there.
Yeah.
All right. Chapter 21. We've got 10 minutes.
Magnets.
Magnetism. Good, magnets. Give me some stuff you know about magnets. Give me some stuff you know about magnets. Some facts.
North and south.
Good. Start with north and south.
Two poles when you break them in half.
Yeah, if you cut in half, you still get two magnets. Why is that?
Does that have to do with the domain, like realignment?
Because poles always come in pairs.
Yeah, poles always come in pairs. And the magnetic domain theory and the alignment. Remember, all of the bonds are polar here. So everything's polarity is toward the North Pole. Well, if you break it, you still have polarity. Okay? What else do we know? What's that? Permanent magnets. How is a permanent magnet made? I need a tissue. I'm dying right now. They do. They create their own magnetic fields.
With external
However, is like a
Yeah, it has to be what kind of material? Ferromagnetic. Hold on. Much better. So, if a material is ferromagnetic and it is put into a Mike, stop. If a material is ferromagnetic and it is placed in a magnetic field, by induction, that material can become a permanent magnet. Now, an example was with the solenoid and electromagnet. We'll talk about that in a little bit. The other stuff about magnets we need to discuss. Field lines. What do we know about field lines? Yeah. The stronger the field is, the more dense they are. Hold on for a second. Because that's with the current in a wire. So, we know that the field lines are going to go from north to south. Now, please don't forget, field lines, you don't see them, but they do exist inside. Okay, these field lines continue. It's a loop, all right? It's a loop. Now, the right-hand rule tells us what, Reese?
That it'll go around, like when you wrap your right hand around a wire, then the flow of the current, right, of the magnetic
Field.
will go the same way as your hand is turning.
So there's the current right there going through a wire. Place your thumb in the direction of the current. Okay? And look at your fingers curl. See the way they curl out of the board on the left? So it's going to look like this. Okay, that's the magnetic field strength.
Wait, so that's one of the purple ones, or one of the red ones, or pink, whatever color is inside that.
It's similar to that. A magnet creates a magnetic field. These field lines are the same idea. Okay, same idea. It's not the same though, because this is a magnet, this is an electric carrying current.
Oh, okay.
When we loop the wire, we create a solenoid, and that's where we'll talk about how it's like a magnet. It's analogous. Let's loop the wire now. Everybody, loop the wire. Do this. Okay? And what you'll have is the current now flowing around that bend and back around here. Now, put your thumb in the direction of the current on this side, please. The current is going to flow this way, right? Into the page on the left and out of the page on the right. So it's going to look like this for the field. So what we notice is that both of these fields are coming out of the center. You see that? Both fields are coming out of the center. When that happens, it is analogous to a magnet. See how here my point. See how both of the field lines come out of the North Pole and loop back around? See how both of these come out the middle and loop back around? It's as if you had a magnet here. And this end is like the north end and this is the south end. It comes out the north and back in the south. Out the north, back in the south. When you loop enough of these wires, you get a solenoid.
Is that the perpetual magnet?
And that's how you can create an electromagnet. Okay, so what happens here is you get your magnetic field looping out like this. This is assuming the current is flowing up the wire like this and out of the wire like that. Okay, there's the current flowing. This acts as a north pole, this acts as a south pole. The magnetic field continues through the solenoid. What do we know about the magnetic field strength? Where is it greatest with the solenoid? In the solenoid itself. Because those field lines are so close to each other. They're going to be very closely spaced. Whereas outside, I'll draw more field lines. Yeah, they get wider and wider. See that out there? But in there, they're really close.
Mr. Howell, you said that the more field length you have, the more strength it has.
The more dense they are, the more close they are. What else do I know? What else increases the strength of a solenoid? Yep. You put a ferromagnetic rod or piece of metal in the middle of it that is not a magnet. It can become a magnet because it becomes a permanent magnet when it's in the magnetic field. Therefore, it gets stronger. Because now you have like a magnet within a solenoid. What else? What else? What else increases the strength of a solenoid?
The length of the cable.
Not close, not length.
Thickness, or space in between the thinness of the space.
Kind of, but
Lateral
indirectly.
space.
Put a rod in between there or something?
Already said it.
Um,
It's the number of coils. So Ed, you could say they're closer together, there's more coils, sure, but it's the number of coils, not the length itself. The length does help because the coils are larger, but it's the number of coils. Now, there's one other thing.
the number of coils do what?
Huh?
The number of coils do what?
Increase. The more coils, the stronger the solenoid. Last thing. What is creating the magnetic field, guys? What is?
You don't want to hear my answer, sorry.
Ah, I could hear you. What is creating the magnetic field? Science. Nick.
The arrangement of the dipoles in the material.
Okay, but that's with a magnet, yes, but with the solenoid specifically. If I don't have what? I wouldn't have a solenoid. The current. Without current, there's no solenoid, right? So the stronger the current, stronger the electromagnet of the solenoid itself. As I increases, the strength increases. More current, stronger solenoid. It's not really called an electromagnet until you take some sort of ferrous material or ferromagnetic material and put it down the center. Okay, now you created a magnet there out of that ferromagnetic material. Like
What exactly is ferromagnetic?
something that can be made a permanent magnet very easily.
But it's not
Something that
a magnet
contains
by itself.
iron.
But it's not really a magnet by itself.
It's not naturally occurring as a magnet, but it can be easily induced to be a magnet. How about the Earth? What about the Earth? What the heck?
So when you're really going north, you're going south, something like that.
Yeah, north and south are switched in that sense, yes. So here's the North Pole, here's the South Pole. The North Pole is really what?
South magnetic.
Magnetic south. Now, magnetic south and magnetic north. Now, look at a compass on the earth. The North Pole on a compass points you to the North Pole, right? Okay, because it's attracted to magnetic south. Hey, the faster the earth spins, what happens? The stronger the magnetic field around a planet if it spins faster. What else about the earth? That's it. Okay?